Basic electricity, direct current. Number 4. Ohm's law in action. In the last program, you were shown how to safely use both an ammeter and voltmeter to determine the amounts of current and voltage in a circuit. Now, in this program, you'll bring together every concept you've learned about electricity by using the meters in a simple experiment that tests how changes in voltage and resistance affect current. This way, you can see for yourself Ohm's law in action.
You've already learned that there is a relationship among the three fundamental qualities of electricity. Specifically, Ohm's law states that current is directly proportional to voltage and inversely proportional to resistance. This fact can be represented by a simple formula. Resistance equals voltage over current. Or, using our standard abbreviations, R equals E over I. You can also state Ohm's law as ohms equals volts over amperes, with the abbreviations omega equals V over A. For example, if the voltage is unknown at 6 volts and the resistance is unknown at 3 ohms, the current is 2 amperes. However, if you decrease the resistance to 2 ohms, the amount of current rises from 2 to 3 amperes. And if you increase the voltage from 6 to 12 volts while keeping the resistance at 2 ohms, the current jumps to 6 amperes. Now let's do some hands-on experiments so you can use this same formula.
To begin, build another DC circuit, but this time use a variable power supply as the power source. The reason for using the power supply is that it will enable you to more easily and accurately vary the amount of voltage in the circuit by simply adjusting the voltage control knob. In addition, fixed ceramic resistors will be used as the load in the circuit. They will be used because they are both inexpensive and a more precise resistor than a light bulb. That is, the resistance level of a bulb actually changes with its operating temperature. However, the resistance level of this 1 ohm ceramic resistor is usually constant at 1 ohm. This consistency of the ceramic resistor makes it better suited for this experiment. Looking at the schematic, you can see that a 4-volt power supply will connect directly to the ammeter. The ammeter will be connected to a 2 ohm resistor and a single-pole knife switch. The switch will be connected to the positive terminal of the power supply.
Start by first making sure the power supply is turned off or unplugged. Then attach a wire from the negative terminal of the power supply to the negative terminal of the ammeter. Continue by attaching another wire to the 5 ampere post on the ammeter. Why the 5 ampere terminal? Remember, if you're not sure of the amount of current in the circuit, always start with the highest value on the meter to protect the equipment from an electrical overload. Next, attach a 2 ohm resistor. This resistor has a simple screw-type post soldered to each end. Add another wire to the other end of the resistor and attach it to the knife switch. Finish up with a wire from the knife switch to the power supply. Now the circuit is ready, and it's time to turn on the electricity. But first, make sure the switch in your circuit is open before turning on the power supply. After turning on the power supply, adjust the voltage control knob so that the built-in voltmeter is reading the 4 volts that were specified on the schematic. Once you're set, close the switch and observe the results on the ammeter. It reads about 2 amperes.
Since this is an experiment, you'll need to jot down the results in table form on a piece of paper. To do this, make 3 columns labeled voltage, current, and resistance. In this first experiment, you'll be varying only the resistance, while holding voltage constant. Therefore, fill in the number 4 volts under the voltage column. Now, fill in the first line of your table. Under resistance, write 2 ohms with a current reading of 2 amperes. Let's increase the resistance and see what happens. Looking at the schematic, you'll need to add a 1 ohm resistor between the first resistor and the switch. Again, open the switch and then open the circuit where you'll install the resistor. Once everything is set, close the switch. Notice the results on the ammeter. It's reading about 1.3 amperes. Now, record the data on your table. Total resistance equals 3 ohms, and the current is 1.3 amperes. Interesting? Let's add another resistor.
Looking at the schematic, you can see that another 2 ohm resistor will be added. Again, turn off the power and then open the circuit to add the third resistor. Make sure all the connections are tight. With this third resistor, the total resistance in the circuit is now 5 ohms. On the table, add the number 5 ohms, then turn on the power. The ammeter is now reading about 0.8 amperes. Record the value. It should be pretty clear that as you've increased the amount of resistance in the circuit, you've decreased the amount of current flow. Let's add 1 more resistor.
Checking the schematic, you can see that another 1 ohm resistor will be added, giving this circuit a total resistance of 6 ohms. Open the circuit and add the final resistor. Add the ohm figure to your table, then close the switch. The ammeter is reading between 0.6 and 0.7 amperes. Now that you've filled out 4 lines of data on your table, let's analyze the results.
Notice that the current has decreased from 2 amperes to about 0.6 amperes, while you've increased the total resistance from 2 ohms to 6 ohms, all the time leaving the voltage fixed at 4 volts. This relationship between the current and resistance is called an inverse proportion. And according to Ohm's law, current will decrease as resistance increases, because voltage E is always equal to current I times resistance R. This is the mathematical symbol that means proportional. By using it, you can state in concise terms what you have just demonstrated. Namely, that current is proportional to 1 divided by omega. Before we start the second part of the experiment, let's introduce the concept of watts.
Remember that amperes, unlike volts and ohms, is a measure involving time. It is therefore a measure of the rate at which something is happening. Watts also is a measure of rate, the rate at which the load uses electrical energy. 1 watt is the amount of power a load uses when 1 volt causes 1 ampere of current to flow through the load. To state the same thing mathematically, watts equals volts multiplied by amperes. Notice that resistance is also inversely proportional to voltage when it comes to determining watts. Graphing this inverse proportion, you can see that as the wattage rating of a light bulb increases from 25 to 50 to 75 watts, the resistance level decreased accordingly. In summary, a 75-watt bulb is brighter than a 25-watt bulb because it offers less resistance, thus allowing for a greater amount of current to flow through it.
In the second part of this experiment, you'll be holding resistance constant and varying the voltage to see what effect it has on current. This schematic shows you that you'll be using the same circuit as you did in the first experiment, with the resistors in place. However, this time you'll be varying the voltage from 4 to 8 to 12 and finally 14 volts. Again, let's keep a record of the data so you can see the results in table form. Set up your table's columns for voltage, current, and resistance. Go ahead and enter the values for resistance. It will stay the same at 6 ohms.
After you've made sure the circuit switch is open, adjust the voltage to 4 volts. Close the switch and record the result. It's between 0.6 and 0.7 amperes. Record the data in the table.
Now, open the switch and turn the voltage up until the meter reads 8 volts. Close the switch and read the ammeter. It reads about 1.3 amperes. Record the data.
Turn the voltage up to 12 volts. Close the switch on your circuit and read the ammeter. It's at about 2 amperes. Record the data. Finally, with the voltage at 14 volts, close the switch and read the ammeter. It's reading about 2.3 amperes of current. Record the data. Now, looking at the results, you can easily see that voltage and current are increasing together. This increase is proportional, and the mathematical formula for the relationship between current and voltage is expressed as current, I, is proportional to voltage, E. You have now learned Ohm's law and demonstrated exactly how it works in actual practice. You did this by first changing resistance from 2 to 6 ohms, and then by varying voltage from 4 to 14 volts. Here's a little trick that will help you remember how to use Ohm's law.
Draw a circle and write the letter E in the top half, with the letters I and R below. Now, if you want to solve for E, just place your thumb over it and solve for what's left. I times R. If you want to solve for R, just put your finger over it and figure out E over I. Finally, if you don't know I, cover it and solve for E over R. Now, let's review the key points of this program.
Number 1. Current is directly proportional to voltage. As you increase current, you increase voltage.
Number 2. Current is inversely proportional to resistance. The higher the resistance, the lower the current.
Number 3. Watts is a measure of rate, the rate at which a load uses electrical energy.
Number 4. Ohm's law is the most important single law of electricity.